Good morning, student. Today we are going to learn about quadrature amplitude modulation, means QAM. In short, we can say it QAM. After the completion of today's session, you are able to define quadrature amplitude modulation, explain the generation and detection process of quadrature amplitude modulation. So, as we know, in amplitude modulation, one message signal is modulated, which is in analog form. But in AM, channel bandwidth is not effectively utilized. So, this can be overcome by using this QAM technique. QAM can utilize in analog modulation and also in digital modulation concept. So, in digital modulation, QAM is the combination of ASK and PSK, and in analog modulation, QAM is the combination of AM and PM. Okay. So, in QAM, we can modulate two individual signals and transmit it to the receiver level. QAM can able to transmit two signals over the same channel. So, this QAM technique also known as quadrature carrier multiplexing. Okay. So, this is generation of QAM signal. So, this QAM transmitter consists of two product modulators and a local oscillator, which is present here, that gives the carrier signal, that is A cos 2 pi fct. So, here we use two incoming signal. As we discussed before, that QAM can modulate two signals at a time and transmitted through a single channel. So, to product modulator 1, we give x1 of t and the carrier signal, and to the product modulator 2, we give incoming signal x2 of t and the phase shifted carrier. Here the carrier is 90 degree phase shifted before given to the product modulator 2. So, to the product modulator 2, we give A sin 2 pi fct, because after shifting 90 degree, as per the mathematical formula, we get A sin 2 pi fct. So, the product modulator 1 with the carrier from the local oscillator form the in channel. This path is known as in channel or in phase channel. Okay. And here this channel is known as quadrature channel. Why it is quadrature channel? As the carrier given to the product modulator 2 is 90 degree phase shifted. 90 degree is the one quadrature. So, this one is the quadrature phase channel or Q channel, and above is the in phase channel, that is I channel. Next, here output of the product modulators are added. So, at the output of this adder, we get the QAM signal. So, the QAM signal is S of t equal to x1 of t into A cos 2 pi fct. Then we add the signal plus with the output of the product modulator 2. So, x2 of t A sin 2 pi fct. So, this one is the output of the QAM transmitter, or we can say it is a modulated signal or multiplex signal, as two signals are mixed and transmitted over a single channel. Next is the detection of QAM signal. So this one is the receiver section. Receiver section also consists of two product modulator and local oscillator, 90-degree phase shifter with two low pass filter. So the received QAM signal is given to both product modulator, that is product modulator 1 and 2, and to the other input of the product modulator we give the output of the local oscillator directly to the product modulator 1 and 90-degree phase shifted carrier signal given to the product modulator 2. So here we give sine 2 pi fct. Okay. Then the output of the product modulators are given to the low pass filter, whose cutoff frequency is set to the frequency of the modulating signal. So it only allows the FM, means modulating frequency, and reject all other frequencies. So output of the low pass filter is half A x1 of t and here half A x2 of t. As we know, x1 of t is the incoming signal given to the product modulator 1 and x2 of t is the incoming signal given to the product modulator 2 in the transmitter section. So here if the output of the product modulator 1 is x1 of t and this one is the x2 of t, then product modulator just simply multiply the input signals given to it. So multiplex signal into cos 2 pi fct. So we transmit the signal, this one, as we discussed earlier, that x1 of t a cos 2 pi fct. 2 pi fc means omega c, so I write here omega c. So a cos omega ct plus x2 of t a sin omega ct. Then it is multiplied with the carrier signal. After solving this equation, here x1 of t a cos square omega ct, cos square means cos square theta, that is 1 plus cos 2 theta by 2. So using that formula here we write this, and a sin omega ct into cos omega ct. So if we multiply 2 and divide 2, then 2 sin omega ct into cos omega ct is the sine 2 omega ct. So here we write the term using that formula. Okay, means this one, the formula sine 2a equal to 2 sine theta into cos theta. Okay, sorry, a sine 2a equal to 2 sine a into cos a. This formula is used here. So here is the final equation of product modulator 1, that is x1 of t a by 2 plus x1 of t a by 2, then into cos 2 omega ct plus x2 of t a by 2 sin 2 omega ct. As the output of the product modulator 1 given to the low pass filter, the low pass filter only allow the frequency of the modulating signal. So this one is contains only the frequency of the modulating signal, the other are rejected by the low pass filter. So low pass filter 1 at the output gives x1 of t a by 2. Okay, See here, x1 of t a by 2. Then the product modulator similarly multiplies the signal, that is x1 of t a cos omega ct plus x2 of t a sin omega ct whole into sin omega ct. As 90-degree phase shifted carrier is given to the input of product modulator 2, so then we solve this accordingly using the formula, that is sin 2a and cos square theta mathematical formula. Using that formula we solve this, and this one is the final equation. So here also it only allow low pass filter to this one and reject these two terms. So LPF 2, at the output we get x2 of t a by 2. So this one is the final output or modulating signal that we get at the receiver section after demodulation. So this is all about QAM. Thank you.